Hey everyone, and welcome back to the channel. Today, we re-dive in deep into a topic that is the absolute backbone of computer science and software development. Algorithms. Now, I know what some of you might be thinking. Algorithms? Isn't that just for getting a job at a big tech company? Well, yes and no. While they are crucial for technical interviews, understanding core algorithms makes you a fundamentally better, more efficient, and more creative programmer. No matter what you're building, think of them as your secret weapon, your toolkit for solving complex problems elegantly. So, grab your favorite drink, get comfortable, and let's explore the algorithms that every programmer should know. First up, let's talk about the bread and butter. Sorting and searching algorithms. You use these every single day, even if you don't realize it. Every time you search for a file on your computer or see a list of products sorted by price, these algorithms are working behind the scenes. Let's start with searching. The most basic one is linear search. Imagine you have a messy pile of books, and you're looking for a specific title. You'd have to pick up each book, one by one, until you find the one you want. That's a linear search. It's simple, but if your pile of books is massive, it's going to take forever. It checks every single element in a list until it finds a match or reaches the end. This is where binary search comes in, and it's a game changer. But here's the catch. It only works on a sorted list. Think of a dictionary. If you're looking for the word program, you don't start at A and flip every page. You open it somewhere in the middle, see you're at M, and realize program must be in the second half. You repeat this process, cutting the search area in half each time until you pinpoint the word. It's incredibly fast. While linear search's time can grow in direct proportion to the size of the list, binary search's time grows much slower. This difference is colossal for large data sets. Now for sorting. One of the simplest is bubble sort. It repeatedly steps through the list, compares adjacent elements, and swaps them if they are in the wrong order. The larger elements bubble up to the end of the list. It's easy to understand and implement, which makes it a great starting point for learning. But honestly, it's very slow for any real-world application. A much better choice is merge sort. This one is a classic example of a divide-and-conquer strategy. It works by breaking down a list into several sublists, until each sublist contains only one element which is, by definition, sorted. Then, it repeatedly merges these sublists back together in the correct order until you have one single sorted list. It's like sorting small piles of cards first, and then merging those sorted piles. Merge sort is stable and highly efficient, making it a reliable workhorse for many sorting tasks. Then there's quick sort, another divide and conquer superstar. It picks an element as a pivot and partitions the other elements into two groups, those less than the pivot and those greater than the pivot. It then recursively applies the same logic to the subgroups. On average, quicksort is often faster in practice than merge sort because it has lower overhead. However, its worst-case performance can be as bad as bubble sort if you're unlucky with your pivot choices, though this is rare with good implementation. So, if you need guaranteed performance, merge sort is your friend. If you want something that's typically faster, quicksort is a great bet. Alright, moving on from sorting and searching, let's venture into the fascinating world of graph algorithms. Graphs are everywhere in programming. Social networks are graphs of people. Google Maps is a graph of locations and roads, and the internet itself is a giant graph of web pages. Two fundamental ways to traverse or visit every node in a graph are breadth first search, or BFS, and depth first search, or DFS. BFS explores the graph layer by layer. Imagine dropping a stone in a pond. The ripples spread out evenly in all directions. BFS does the same. It starts at a source node and explores all of its immediate neighbors first. Then, for each of those neighbors, it explores their unexplored neighbors, and so on. This is incredibly useful for finding the shortest path between two nodes in an unweighted graph. For example, finding the fewest number of connections between two people on a social network. DFS, on the other hand, explores as far as possible, down one branch, before backtracking. Imagine you're in a maze. You'd probably follow one path until you hit a dead end, then backtrack to the last junction and try a different path. That's exactly how DFS works. It uses a stacked data structure, either explicitly or through recursion, to keep track of where to go next. DFS is excellent for tasks like checking if a graph has cycles, or for solving puzzles like mazes. Now, what if the paths in your graph have weights, like the time it takes to travel between cities on a map? For this, we need something more powerful. Enter Dijkstra's algorithm. Dijkstra is the go-to for finding the shortest path from a single source node to other nodes in a weighted graph. As long as there are no negative weights, it works by maintaining a set of visited nodes and continuously selecting the unvisited node with the smallest known distance from the source. It's the algorithm powering many GPS and network routing protocols. It's truly one of the most beautiful and impactful algorithms ever designed. Let's switch gears a bit and talk about a powerful algorithmic paradigm. Dynamic programming, or DP. Don't let the name intimidate you. The core idea is actually very simple. Break down a complex problem into simpler subproblems, and store the results of these subproblems so you want to have to calculate them over and over again. A classic example is calculating the Fibonacci sequence. The nth Fibonacci number is the sum of the two preceding ones. A naive recursive solution would recalculate the same Fibonacci numbers many times, leading to an exponential explosion of work. With dynamic programming, we can calculate each number just once and store it in an array or a hash map. When we need it again, we just look it up. This technique of storing results is called memoization. Dynamic programming is all about optimization. It turns problems that seem impossibly slow into ones that can be solved efficiently. It's used in a huge range of applications, from bioinformatics for sequenced alignment to finance for asset valuation. Recognizing when a problem has overlapping subproblems and optimal substructure is the key to unlocking the power of DP. Next on our list are hashing algorithms. Hashing is a technique used to map data of any size to a fixed size value, called a hash code or simply a hash. This is done by a hash function. A good hash function will generate a unique hash for each unique input. Though collisions where two different inputs produce the same hash can happen. Where is this used? Everywhere. The most common application is in hash tables, or hash maps, which are data structures you probably use all the time, like dictionaries in Python or hash maps in Java. They allow for incredibly fast average case lookups, insertions, and deletions. When you want to store a key-value pair, you hash the key, which gives you an index in an array where you can store the value. To retrieve it, you just hash the key again and go straight to that index. It's like having a magical address book that tells you exactly which drawer to open without searching. Hashing is also fundamental to cryptography and data integrity. Cryptographic hash functions are used to create digital fingerprints of data. If you change even one tiny bit of the original data, the hash will change completely. This is how you can verify that a downloaded file hasn't been corrupted or tampered with. Finally, let us touch upon a category of algorithms that are incredibly important in modern AI and data science. Greedy algorithms. A greedy algorithm makes the choice that seems best at that moment. It makes a locally optimal choice in the hope that this choice will lead to a globally optimal solution. Sometimes this works perfectly. Consider making change with the fewest number of coins. If you need to give back 68 cents, the greedy approach is to take the largest coin possible that is less than or equal to the remaining amount. You take a 50-cent piece, then a 10-cent piece, then a 5-cent piece, then 3 1-cent pieces. In this case, the greedy strategy gives you the optimal solution. However, greedy algorithms don't always yield the globally optimal solution. They can get stuck in a local optimum and miss the bigger picture. But for many problems, they provide a very good approximation that is much faster to compute than finding the perfect solution. They are used in scheduling problems, in some graph algorithms, like Kruskal's, for finding a minimum spanning tree, and in data compression, like Huffman coding. So there you have it. From searching and sorting to graphs, dynamic programming, hashing, and greedy approaches. This is by no means an exhaustive list, but these are the foundational pillars. Understanding them doesn't just mean you can solve interview questions. It means you can analyze problems more effectively, choose the right tools for the job, and write code that is efficient, scalable, and elegant. It changes the way you think about problems. My advice? Don't just read about them. Implement them yourself. Pick a language you're comfortable with and code them from scratch. Try to solve problems on platforms like LetCode or Hack. It's the best way to truly internalize these concepts. I hope this overview was helpful and got you excited about the world of algorithms. They are the art and science of problem solving in the digital age. If you enjoyed this video and want to see more deep dives into specific algorithms, let me know in the comments below. Don't forget to like, subscribe, and hit that bell icon so you don't miss our next video. Thanks for watching, and happy coding.